Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. So today we are going to learn how to do response spectrum analysis and subsequently do the design of the structure. So we are in week 12 and this is our 6th lecture in this series. Now before we go into the details of response spectrum analysis, let us first quickly see why we need this analysis. Recall, earlier we have done ESA where the first assumption was that the building was regular type, and we also made some assumptions on TA, if you recall, and then we completed the design. Now, a better approach, of course, is using response spectrum. Now, the first question that we have to answer is, what is a response spectrum? Now, again, we will not go into the very details of this theory, but broadly we'll see what is the meaning of this response spectrum and why it helps particularly in earthquake analysis. Now, let us again continue our discussion with the 2-DOF system that we used to derive the equation of motion, if you recall. So, here is the system. We have two masses, M1 and M2. And we have lateral stiffness K1 and K2. K1 is not the stiffness of this column alone, it is the combined stiffness of two columns in the lateral direction, and the degrees of freedom x1 and x2. Now, if you recall the equation of motion that we derived earlier, mx double dot plus cx dot plus kx is equal to f. Now, this is a coupled equation and we decoupled this equation also using x equal to phi z, this transformation. Then, in the modal coordinate, we have the equation mdi zi double dot plus cdi zi dot plus kdi zi is equal to f di. So, this is in the modal coordinate. So, this is the ith modal coordinate. Now, it has a certain advantage because effectively this is a SDOF system. Okay. So, we can easily solve this equation and find out what is Zi of t. So, this we can easily find out from this uncoupled equation. However, solving this equation is really difficult because this is a coupled equation. Now, for a large scale building that we have modeled previously instead, you can sense that solving this coupled equation with all degrees of freedom is very difficult. It's possible, we'll also do that, it's possible, but a better approach is using modal solutions. Now, when we transfer that into modal equation, then each and every mode provides a SDOF system and that we can easily solve, right? In fact, this equation is solved in time domain. We can also solve it in frequency domain. But for the time being, if we even solve it in time domain, we get the response. Say, typically this is the response, right? So, this is t and we have here zi of t. So, I will range from 1 to up to n, as many modes we consider. It's the number of modes for that particular structure. So now for this 2-DOF system, if I write the equation, what we have, x1, x2, both of them are function of time, which is equal to, we have phi matrix, phi 1 1, phi 1 2, phi 2 1, phi 2 2. Now that is multiplied by z1 t and then z2 t. So if I focus say top floor response x2 t, from this right hand side expression, what we can write, it is phi 2 1 z1 of t plus phi 2 2 z2 of t. Now you can see we solve this modal response and then linearly add them up to get the actual response. Now we have already solved this modal coordinates. Now just imagine if this is the maximum value of this zi, then what we can do, if we need to find out x2 max is equal to phi 2 1 z1 max plus phi 2 2 times z2 max. So what we can think of, that this maximum value of the z, if we find out for all modal response, then we can easily find out the maximum value of the top response. In fact, this maximum value we are interested of in design, not the complete time signal, as you can see here. Now, of course, you can raise a question that what is the guarantee that when this will be maximum, simultaneously z1 and z2 will be maximum? Yes, that is absolutely true. But for the time being, we can assume that. We will see, we will use a technique called SRSS. This is square root of sum of squares. So there are different other rules like CQC. I will alert you when this will come as we solve the building in StatPro. So right now what we have absolute summation. Okay. Now the point to be noted here, in this expression, this is extremely important, because in this expression we don't need to solve x2 from this coupled equation. Instead, what we can do from the modal solution, which is effectively an SDOF system, and then from that we can actually find out the peak response of the degrees of freedom we are worried for our design purpose. Now, with this logic, let us see if we have a SDOF system, because effectively in the modal coordinate we are solving all SDOF system, right? So if we have a SDOF system which can be idealized like this, then for this SDOF system, or let me write z of t. So this is say kd, cd and md. So we can find out the response z of t, and we need to store the maximum value. Now imagine what is the natural frequency of this system. Omega d is square root of kd by md. Now imagine if we change this omega d, or from omega d we can also find out time period td, which is 2 pi by omega d. So if we change this over a wider range, and then for each value of omega d, that means we keep the mass constant and then we change the stiffness so that omega d changes, and for a certain percentage of damping ratio we are not going into the details of that because that is for the time being not required. Just imagine that CD is fixed to a particular value CD star. Then on the x-axis we have either we can plot omega d, or normally instead of omega d time period is plotted. Then what we'll get, for each of them we get the maximum response solved from here. So from there we get the maximum response corresponding to each time period, right? Then if we connect this, what we have on the y-axis, it is Z max. So the maximum response, it can be displacement, it can be velocity, it can be acceleration. For the timing, let us consider displacement, or we can also consider acceleration, because from this zt we can actually find out acceleration. So if just I plot the z double dot max, then we can also do that. Just instead of plotting displacement, just plot acceleration and then find out peak acceleration. Now this diagram is called response spectrum. What is the advantage of this diagram? Again I repeat, we can plot either displacement or velocity or acceleration. Accordingly, we have to find out the response of the SDOF system, and then we have to plot this maximum value. In fact, we can plot all of them together in a single plot. That again, we are not going into the details. So the advantage is, you see, this is the maximum response corresponding to each time period of the SDOF system, right? And of course, there are other definitions. For example, if this is an acceleration spectrum, there is a plot called pseudo acceleration spectrum. We are not going into the details of that. That is not required for the time being. Now, what is the advantage of this? Advantage is, let me rewrite this expression again. So we have x2 of t is equal to, we had phi21 z1 of t plus phi22 z2 of t. So this are the modal response corresponding to a frequency. So this is omega 1, or we can call it using the time period. This one corresponding to omega 2, and the corresponding time period is t2. So if this is the time period t1 and t2, we can identify, say this one is t1 and say this is t2. So we can identify this maximum response, and from that maximum response we can easily find out x2 max. See how easily we do it. And we generate this response spectrum once and keep it ready. It has nothing to do with your actual structure because it comes from the SDOF system, right? So that response spectrum is ready. Of course, for that we have to apply a particular earthquake here and find out the peak response here. So this response spectrum is for a particular CD and a particular xg double dot of t, right? So we set the damping level and set the input acceleration and then find out the maximum response of the SDOF system that we plot, and that is the response spectrum. The advantage is, now we can use this plot to find out the peak response. And just imagine if we have 5 different earthquake. So here we have T, and here if we have say Z double dot, then we have maybe 5 such plots. Okay. Now we can take the average, and then we can, instead of all these plots, we can take the average. Let me erase it because otherwise it is not visible. So we can plot the average and then do some processing. We get a plot like this, and this is what is called design response spectrum. Okay. Design response spectrum. This is what we see in our code. Again, developing design response spectrum, it has certain procedures. We are not going into the details. The concept is you consider a few different earthquakes and for each of them develop the response spectrum and then in certain average sense develop this plot. I will show you the design response spectrum in Indian Standard Code in a minute, but from this plot, as I showed here, you find out the response corresponding to the time period of the structure. So if you have say 2 degree of freedom system as we have in this example, so corresponding to each time period, let us find out these values and that we use for finding out the response. Now, what is the advantage? There are certain other advantages, but the first advantage, without going into the mathematical details, from this logic you can easily appreciate that we don't need to solve the complete structural systems and this is already provided in the code, and using this code we can find out what is the peak response and that is what we are going to use for our design. Now, with that background, let us see what we have in Indian Standard Code. So now I have already shown you this code that we are going to use today for response spectrum based design. Now in this code, it actually talks about the design response spectrum that we'll see in a minute. So for the ground motion, we actually generate the response spectrum, and then why we need to do? Because earthquake loads are dynamic loads that actually introduces an inertia force leading to vibration, right? However, we are right now doing linear dynamic analysis, and as per this code, we have different seismic zones, as you are all familiar with right now, and then so long the dynamic analysis is concerned, we can either perform response spectrum analysis that we are doing today, or we can also go for time history methods. Okay, so we'll see both of them using STAAD.Pro. Now, this method, of course, it is better compared to the other one, ESA, we have already covered in the previous lecture. So when we do the response spectrum analysis, I have already explained to you what is the meaning of response spectrum. It is actually the peak response of a SDOF system, right? And that provides you the response spectrum. And of course, from that response spectrum, a series of response spectrums, we develop a design response spectrum. Now, the main advantage is here because it allows you to avoid full time history analysis, and then using this method, you can find out the peak response very easily, and we'll see how we can make multiple combinations in a minute. But here what you need to worry about, the natural frequency, then the damping level, and then of course the acceleration, ground acceleration, to be more precise. Right. Now, why we adopt this method compared to ESA? Recall in the ESA we used a empirical expression of TA. Here for this multi-storied building, these days they are very common, then we can go for a precise model analysis and find out the frequencies. And I have already shown you the model participation factors and higher modes present in the model analysis. So it can actually capture the effects of higher mode, and there, if you recall, I showed you that in our building, the one we are right now designing, it has a lot of closely spaced modes. Closely spaced mode means two natural frequencies, say omega I and omega I plus 1, they are very close to each other. So if you have closely spaced modes, of course, the formula that we have used for x2 max as the summation of the maximum response of the individual modal response, that is not correct. For this kind of situations, we have a better method called CQC method. Again, we will not go into the details of that because this is not a class on seismic design, but our aim is to consider these forces systematically as mentioned in our code and complete the design, RC design. Now, the moment we consider this modal response of a structure, that means we express x, that is original coordinate, in terms of modal coordinates, we actually consider a realistic distribution of forces along the story, right? So the advantage is we can capture higher modes, we can actually capture closely spaced mode very effectively using this method, and then we can also have a realistic distributions. Now let us quickly go through this IS 1893. So for that, again, it first defines the seismic zone. Recall, for our structure we are in zone 5. Then there is a design response spectrum. So this design spectrum I will show you. Load combinations. Okay, this is extremely important. We'll go through this. In fact, we have to do a lot of load combinations. That is a very tedious task. We have to do that. Now the key parameters, if you recall, in this zone based quantification of the seismic load is the zone factor, then importance factor, response reduction factor, and soil type. For our case, we use medium soil. And of course, in this codal provision, we have 3 different categories of soil: soft soil, medium soil, and hard soil. Now, the spectral shape, you will see the spectral shape of the design spectrum is something like this. And this shape changes as we move from one, soil type to another, and of course the peak response is affected by the zoning of this entire country. So we are here, somewhere here in zone 5. Now recall this horizontal coefficient, we have already used this expression we are familiar with, and now this SA by G. Now if you take this design curve, recall, if this is for acceleration, we have T here and Z double dot maximum, right? Z double dot maximum, because that is the maximum response of the SDOF system. Now if we plot acceleration, we have Z double dot. If we plot any other quantity, we have to take the maximum of that. For the time being, let us assume that this is acceleration. Now this acceleration is called SA. Okay. Now acceleration, if it is divided by G, then we have a unitless quantity, and this SA by G is actually reflected in the vertical axis. And that's why when we earlier used this, I told you I will tell you the meaning of this SA by G when we discuss the design response spectrum. So you can see here, for acceleration response, we have this called spectral acceleration. Again, it has certain meaning. For the time being, it is not required. So spectral acceleration is converted into a dimensionless quantity by dividing it with G, and then we plot it here, and that's why we get this SA by G. Okay. Now again, for zone 5, we have this Z as 0.36, and here is the design response spectrum. As you can see, on the y-axis we have SA by G, and on x-axis we have the natural period in seconds. Now you can see there are 3 different types of soil, and for 3 different types of soil we have 3 different design response spectrum. So these are design response spectrum. Now you can see all of them are actually anchored at 1. That means SA by G is equal to 1 when T is equal to 0. It means that SA is equal to, you can actually tell that it is a Z for that particular case. So Always keep that in mind. It must be anchored at SA by G. Right. Okay. Now, with that idea of response spectrum and why it is important for the seismic design of RC buildings, let us see what are the load combinations. And here you can see the load combinations. This is self-explanatory. We have already done load combinations. Here you can see dead load plus live load plus you have earthquake. EX means we apply earthquake along X, along Y, and in fact you can also apply along Z depending upon the case that you wish to solve. For the time being, let us consider IX and IY, and then you can take it further. You can also, if the need be, add another dimension and apply the earthquake in the vertical directions. Now, here you can see the load factors, different load factors, and you can see this plus minus sign. Okay. So, effectively, we have three different combinations, but because of these plus minus signs, we have to make all of them when we'll do the design. And that's the most tedious part of this. Otherwise, it is very simple. We have to define the response spectrum, which is already there. We just need to select, and then it will automatically do the analysis. Only the load combinations we have to prepare with these appropriate load factors. So, with that, let us move over to our STAD modeling. Okay, so now you can see the model that we developed earlier. So here, earlier we solved using equivalent static analysis, if you recall, and we designed it completely, but we'll design it again today using response spectrum approach. And for that, again, we have done the modal analysis earlier, and if you recall, the first natural frequency was 3 point something. I will check it again today, but you'll see for this building, we have done the modal analysis, and we solved for first 25 modes along with their participation factors, right? Now, so for this structure, we have to define the response spectrum. For that, again, we are using IS code. So let us go to the load combinations. And here, for the previous design, we have already done based on IS code. And here you can see different mass reference that we used earlier. Now, when we go to the load combination, we have all these load cases. Now, these load cases, for the time being, it was automatically generated. What we do, let us delete this load case, and then we have to redefine the load cases according to the combinations that I have already shown you. Now, for the seismic load, we again use IS 1893. It is already selected, and here you can see we applied it along EQX and X direction and Z directions, right? So, first thing, we will actually delete these load cases. So, you can do it one by one. A better way is to go to the text file, and in this text file, we have all the load cases. You can see on the screen from load case 7 to load case 20, it is here. So, these load cases we have to delete. Okay. So, once you delete this load case, we have ESL load cases also. Load case 1 and 2, let us delete that. And now the dead load case will be 1 and the live load case will be 2. So let us renumber them. Now, we can also remove the modal analysis because we will directly go to the response spectrum analysis. And for that, all the load cases are removed. Now we have to define the load case again. So we have the dead load and live loads renumbered. So now let us add seismic load case and we call it RSA along X. Similarly, we define RSA along Z. As I told you, we are not going to apply the vertical acceleration. If the need be, you can repeat the same procedure and apply the vertical acceleration as per the codal provisions. Now, we have these two response spectrums defined. So, for the first one along X, let us select a response spectra, and here you can see you can actually define your own custom response spectrum. By default that is there, and along with acceleration or displacement, these are the two different types of response spectrum you can, and then interpolation type also you can select. Here you see we have different options. Custom made response spectrums are given here. For each and every time period you have to define the acceleration level. However, in our analysis we select IS 1893. And the next one, you see the combination rules. ABS you are familiar with, I have already explained, and you can see SRSS is there, CQC is there, and different other options are there. For the time being, let us select SRSS. And then we have subsoil type. So from this classification list, let us select medium soil. And then we can apply the direction. We have selected acceleration response spectrum. So we have to apply along X because this load case corresponds to RSA applied along X. So let us select X. And then recall all these factors, and here if you put the factors, AH is 0.036 times SA by G, right? So we have to apply that factor here, 0.036. Similarly, for RZ, we repeat the same procedure. We select the Indian Standard Code and then SRSS rule. For the soil type, it is medium. And this time we apply along Z direction, and again the factor is 0.036. Okay. So the response spectrums are defined. Now we have to go for load combinations, and for that again we select Indian Standard Code and then we generate the load combinations. So we have generated the loads. As you can see here, the same way we did earlier. Here we have, for the response spectrum analysis, again we have generated these different load combinations. Now you see the first one have load 1, load 2 with appropriate factor. Load 1 is the dead load, load 2 is the live load, and then we have the earthquake loads also added. Now we'll make these combinations and manually we'll also define them. We'll show you how to define these load cases. Just notice the factors. So when we combine earthquake response spectrum along X and Z, you see the first combination has 1.2 outside multiplied by all these combined loads. But note that when we consider two simultaneous earthquakes, we have full earthquake applied along X and 30% along the orthogonal direction, right? So now let us go for this combination. You can see the general format is a factor times your load case. So let us use that as per these combinations. So first one is 1.2, but the second direction, that means along the Z, we have to apply 30% of the earthquake. So first factor is 1.2 for the dead load, 1.2 for the live load, 1.2 again for the PSA along X. Then for the other direction, it is 1.2 times 0.3. As you can see in this combination, 1.2 times 0.3 there. So it is 0.36. Right. So now it is applied with appropriate load factors. So if we add, here you see we have the load combination case 20. Now we need to define other combinations following the same steps, but we can do it two ways. So for the second load case, again we can select all of them. Now again define the factors, 1.2 for dead load, 1.2 for live load. Then the first one along Z direction with full load. And now in the X direction we apply 30%, so it is 0.36. So you can see we have a load combination 21 where we flip the response spectrum directions with appropriate factors. So for all other combinations, we can just copy it here and change it and prepare the other load combinations. We have to go for all possible plus minus combinations that I have already shown you, so that we can very easily do it from this text file. We just need to change this to minus sign, and this is the repetition of load case 20 but with the negative along Z direction, you see. Similarly, we have to repeat the same exercise for all other combinations. So let us complete this here, which is very easy to handle rather than defining all of them from the GUI. So now here we have negative, we have some other combinations. So let us do that. Here you see they are already generated and applied. All of them you can cross verify. Just clicking that load case, you can see. So now we'll go to the next load case. So it is 1.5 times 0.3, right? Now here in this we have dead load, RSA along X, RSA along Z. So dead load is 1.5. Then 1.5 for the full load along X. For the other direction, 1.5 times 0.3. So it is 0.45. It's not defined. One point five, 1.5, and then 0.45. So let us add that. Last time I forgot to add. Then we apply full earthquake load along Z and 30% along X. So accordingly, change the load case along with appropriate factor. So let us add it again. So now you can see these two load cases are defined. You have to make again the combinations. So for that, let us go to the text file and repeat the same procedure as we did in case of other combinations. We have to change the load case number because we have just copied from the previous load cases. So we have to change the plus minus signs also accordingly. This will be 34. That is the negative combination when both of them are applied in the negative direction. For symmetric building, we may avoid this plus minus, but because we have a asymmetry in plan, we have to consider all of them as per codal provisions. So now let us save it again and check whether they have been applied or not. Here you can see we have load cases up to number 35. And just you can cross verify by selecting the load case, and from the drop down you can check the appropriate factors and make sure that the factors are applied according to the combination. So now the last one, you see we have 0.9 dead load and 1.5 times the summation of the earthquake in X and 30% in Z. So let us complete that exercise. Dead load, RSA X, RSA Z. For dead load, the factor is 0.9. RSA X, it is 1.5. And along Z direction, 1.5 times 0.3. You see, it is here 1.5 times 0.3. So it is 0.45. Let us add. So that's now done. Similarly, we can also apply the other load cases that we'll do in a minute. For load case 38, that is the next load case, we'll have dead load, then RSA-Z fully applied, RSA-X with 30% of its design value. So here RSA-X will have 0.45. So now if we add, we'll have this load case again. So in one case we have full load along X and 30% along Z. The other case it is just the reverse. And then for this load combination also, we have to repeat the same procedure. We'll copy and then change the plus minus sign to define the remaining load cases. So you have to change the load case number along with the negative sign. So now we have to change the sign. This should be 41. It will be negative this time. Repeat the same procedure for the remaining combinations. Now both of them will be minus. And we have to change the load case number. It should be 43. Okay, so with that, we have the complete set of load combinations. Now if you go to the main file, we have all the load combinations for this response spectrum analysis. As you can see, we have up to load case 43. Again, once you apply this load case, just make sure that they are with appropriate factors. And once you apply all the load cases, then it is ready for solution. Here there is a mistake. That's the reason you should check always each and every load combination factors once you define, and then go for the design. Okay, so now all of them are checked, so we can go for solving the case, and let us see the output file the same way we did earlier. We have to first check whether any member has failed or not. If they fail, accordingly we have to modify the design. Here you have eigensolutions, as you can see. And if you look at the values of natural frequencies, they are extremely close. Okay. And we have complete details that we explained earlier. Now you can see we have damping also defined. In this problem, we considered 5% damping. Again, We are not going into the details of damping model, but for the time being, you just note it, it should be 5%. Those who are interested, again, just go through different damping models normally taught in structural dynamics course. Here you can see the modal participation factors. We have up to 72%. We can increase the number of modes to cover higher modes also. Now here you see the details of response spectrum analysis provided. We'll see the design in a minute. Note, we have not applied acceleration along z direction. If the need be, you can apply. And here are the design parameters. If you recall, earlier we defined all of them. Then the response spectrum is defined. Then participation factors. Now comes concrete design. So with the individual beam numbers, we get the details here. So no section has failed in this analysis because it is already designed and the sections are selected accordingly. So if you select the beam, you can see you have the load case number. For example, in this case, we have load case number 33 is critical. And for that, you have the force details and the capacity details. Also, the reinforcement details are given. Likewise, the complete design details for each and every element is provided. So you can go to the post-processing and you can select the load cases, and then for each and every load case, you can see the response of the structure. For example, if you select beam, here you see the load combinations along with the node numbers, and you can also select other load case numbers. Accordingly, you can plot the response. This is the shear force diagram for the individual load as well as for the load cases. You can generate and you can check the values of shear force bending moments. So you can select only one load case, and for that you can check the values for that particular load case. Otherwise, if all of them are selected, then in this list all of them will appear. So you can identify the critical load case number for a particular element, and then for that you can check the response. So you can see shear force bending moments along all the axes are provided. You can also check by selecting a particular element and the response, and here also you can check the critical load combination. And then you can also select the other response quantities like bending along other direction, shear, and accordingly you can plot the graph for that particular element. Earlier we plotted for the complete structure. Here for a particular element you can also check. Now if you select for modal animation also you can do, but more important is the deflection. So now if you select a node, you can actually find out the displacement. Right. So that completes the design using response spectrum analysis. If you have any doubt, do let us know. Otherwise, let us conclude here. In the next class, we will see time history analysis. Thank you very much.